So welcome to class. And last week we were looking at the effects on EM waves, of course, by maybe the obstacles we have around and depending on the environment. So we went through this section where I actually listed them the way they are appearing there, and we looked at the environment, the different types of environments which are outdoor, indoor, and we're able to get the different obstacles which you have in those environments. So that's what we went through. Then from there, we looked at the properties of the different obstacles, which are basically now the media that will be most probably affecting our signals as they propagate. And this is quite important when it comes to spectral management. Then we looked at reflection, where we were able to see what it is exactly and how we use it positively, and also the negative effect which it can have on our signals. Then we did refraction, remember, and we were able to look at also the effects it has, which is usually similar. In fact, most of them are similar to what we had in reflection. Then we also have the next one, which was attenuation. And I looked at this as well. I think I was able to explain on what happens when you're talking about distance and also a number of obstacles which have been introduced, which basically change this variable, which you are calling the attenuation constant. But I will be looking at this more when it comes to losses. And please note that this section here is quite important in wireless communication systems, because it's the one which determines um, how you are going to place your transmitters and how you are going to place your receivers also, at what distance, at what point are you going to put the repeaters, because in most cases you require repeaters to increase the strength of the signal as it propagates. So this section here of attenuation, I will be looking at it again when it comes to losses, which you are basically going to explain more and look at what many people are doing in relation to propagation modeling, where they have come up with quite a number of models that we are using in the design and placement of the communication equipment. So I think I was able to explain this. We'll be able to see the importance of that later as well when it comes to propagation modeling. So the next concept here is scattering. I think this is where we're supposed to start from after having looked at the others. Um, and I went into quite a number of details. So scattering is actually quite similar to reflection. The only difference we have between scattering and reflection is that the signal in most cases will actually be reflected in very many directions, in which case you are looking at surfaces which are basically rough. When you talk about the texture, their texture allows the signals to be reflected in many directions. So there are a number of those scattering types that we have. I'll be able to look at them. We have the back scattering. We have the front scattering. Then there's also the side scattering. So when you have an obstacle, like now maybe I can take this example of a diagram which is indicated here. What will happen is that you're going to have the signal coming in, though this is light, but it works also for all the others, the radio waves and microwaves, and even gamma rays, all of them. All the electromagnetic waves will experience the same effect. Only that it will depend also on the type of obstacle that you are dealing with and the frequency difference. So when it comes in, if it finds an obstacle, some signals will go back to the source, which means that's back scattering. Then when a signal moves still in the same direction as the incoming signal, we call that front. And then when we have it on the side, either this side or that side, we actually call it side scattering. So it's just a type of reflection which we dealt with last week. So you can be able to see there where we're having the different surfaces which are actually smooth. About the texture, you're talking about a rough one. We have a very rough one. Then we have, of course, even higher than the earlier one. And you realize that you're going to have the signals scattered in more directions when the surface is actually very rough, or when you're talking about their texture being quite rough. So this sometimes can also be given in terms of some methods or some um, research which has been done, and they actually indicate that we could be having a number of those scattering types as well in relation to maybe the ones which are indicated here. They're actually taking the names, mostly the names of the people who discovered them. Like you can see here, we have the railway scattering. Yeah, there is the mice scattering. Those two, and I think you can be able to see that this has got a slight difference from this one here, where more of the signal goes in this direction, but here you are looking like a signal going almost in all the directions, in equal magnitude. So how do we apply scattering in relation to spectrum management? Um, the importance is just quite similar to what we discussed under reflection and scattering. I mean, reflection and refraction. And you can be able to see here, I've actually tried to put them down. I listed the ones we talked about last time. I remember we didn't, I was just mentioning, but I actually decided to put them in writing so that they are captured. So when you are repeating the signals, at some point you actually involve the repeaters so that the signal can be able to get to the transmitter so it gets in. Then in most cases, sometimes if it's a passive repeater, what will happen, it will just reflect the signal and it gets to the receiver side. You could also be able to talk about up there in space. In fact, there is a concept which is applied in the transmission of radio waves and also microwaves. Um, we usually have at night, you must have seen some light, and we usually call those ones meteors. So you also have meteorites, but in most cases, when they don't get to the Earth's surface, we call them meteors. These ones can be used in the transmission. When the signal gets to this point, it can actually be refracted and scattered in many directions. That way, you're able to get it in locations which you could actually not be able to receive the signal. So if you have many of them here, like maybe we indicate that that is space, then you send your signal from down here. When it gets to this point, it will be scattered in many directions like that. So because of the scattering, You could be having a receiver here, so we call this a transmitter, and we call this a receiver. So your receiver, all those are actually on the Earth surface, and your signal is able to get to space up there. It gets into contact with these obstacles, then it's scattered. It gets to the other side of the receiver, and that way you're able to receive your signals. So scattering can be important in that perspective, just in a similar way that we had for reflection. So UHF communication, it's a similar concept that is being applied here. You're also talking about interference among. So the prevention of interference among users, usually you actually talk about the separation in terms of frequency. You can also do space and time diversity. This one I mentioned last time as well. So you can talk about constructive reflection, where the signal will add to the received signal or to the transmitted signal, making it more. And that way, because of the strength, which is actually quite high, the signal is able to go more distances. That's what we call constructive interference, which will come also as a result of scattering. So this one I've already mentioned, over long distances. That's actually what's happening exactly. Layers in the atmosphere can also do this, and I call this process ducting. So it can also happen within or in terms of scattering as well. So I think those are some of the indications that we can be able to put in place. Destructive reflection. This one I'm just trying to repeat what we said last week, though it's also related to scattering. In destructive, you can use it in cancelling signals. Please know that when you are talking about places where you don't want a particular signal to get to, or like maybe mobile phones guys are receiving and you have a meeting, you can actually be able to disable that using frequency jamming, as they call it. So you disable mobile phones. I think you have seen a case where the American presidents coming to some of the countries, like when they came to Tanzania the other day. I think who was that? I think most of the presidents, American presidents, recent ones, have come to Tanzania. You realize that they used to block our communication. In fact, your mobile phone could not be able to send, even here in Nairobi, signals because of security reasons, so they could just disable all those systems. By the way, if I may ask, why do you think these guys could want to block mobile phones when they come around? So when like we have an American president visiting maybe an African country as an example, like Kenya or most probably an East African country, why do you think they would want to disable mobile phone communication systems? What's the reason why? An idea? Yes. Mm, yes. Actually, that is one of the main reasons. So usually when they disable the phones, even actually activating uh, those IEDs will be a problem for these guys. So they want to disable as much as possible, and that's the reason. So I think Saitoti indicated security matters. That was what I mentioned, but I wanted specific cases which the two members have given. Yeah, so we have seen that from Ogutu. You're indicating detonation of bombs using mobile phones, but you can also talk about IEDs. Yeah, and I don't know whether some members know what IEDs are. Frida, good morning. Good afternoon, actually, just now afternoon. Do you know what IED is? What IED is? What does IED stand for? Maybe Daniel, you can expand for the members to know what IED stands for. Yes, we didn't get. I think there was a lot of noise. Yeah, improvised explosive devices. That's correct. Usually, you can actually use Arduino. Some guys even use Arduino, which is a device. I don't know whether I've showed it to you. They can be able to use that one to detonate. Those some of them actually will connect through the mobile phone. Others you can use Bluetooth. Yeah, so they can disable those frequencies which they know can actually cause problems. Or guys can be able to use them to remotely control some devices, including even vehicles, and that's one of the main reasons. So I think with terrorism, guys out there are using them. Even in Somalia, you've heard about those things happening. Northeastern here in Kenya, even around in some places currently, of course, though it's reduced, but they used to do that. So you can see how frequencies can also be used negatively, and how you can be able to prevent that from happening sometimes. That is also part of the management process. In fact, you guys, when you're dealing with terrorism, because I know some guys will go straight, will actually be dealing with the same directly. So you also be trained on how to deal with such a kind of cases and systems that you come across, which are being used for the same. So the negative effect, of course, where a signal comes and interferes with the other, if they are of the same frequency, and communication authority can come in to solve that problem. We mentioned it. Of course, here it's indicating this can be intentional or sometimes unintentional. Those frequency interferences, the competitors can do it intentionally. Some of them, um, in fact, like even radio, it does not have even to happen to mobile phone operators. It can also be the same or similarly applied to radios. Because I know there's a time Citizen, I think, jammed the frequency of Kiss FM one time, and it was even in the news. So here now comes in to solve such a kind of problems. So you talk about scattering, which is just quite similar to reflection as we have indicated. So mobile communication systems and the quality of service will reduce. In this case, you need to be able to make sure that something's done so that you avoid the interference from happening, and therefore increase the quality of service. Currently, Safaricom, I think, could be having the highest the other day. Though earlier we used to have Airtel with the highest and maybe Telecom, but I think Safaricom have also picked and their quality has increased. But you realize that because they have very many, you could be having the data. Someone who has the data, what are the specific values currently for those mobile operators? We go to communication authority statistics. You can be able to get those details as well. But let's get what Charles is writing. You could even mention, no problem. So why are the radio stations still asking listeners to reduce their volume when they call stations? Because of feedback. It's usually because of feedback. Feedback. Please note that I want Frida. You can put on your device briefly. Frida, you still there? Yes, yes. Now that's good. Charles, Charles, is your question answered through an example? Frida, you can put it off. Uh, so, Charles, you have gotten the reason because of that feedback. Actually, you realize that when she put on the microphone, there was a lot of feedback. That's exactly what happens when someone is talking transmission. Then you have put on your radio. So you have two different devices which are communicating, and there is that feedback because you are the one who is actually transmitting the signal. That feedback brings a lot of noise. Yeah. Sometimes it also happens with the public address systems. And you're asking, is there no solution to this yet? I believe you guys are doing research on the same, and it must have even reduced. Though this one, it's not quite necessary for you to be able to incorporate so much. Maybe you don't have to do a lot of to use a lot of resources because it happens just once in a while. It's not all the time that it will be happening. It's only when maybe someone is calling the media station, that's when you have that effect. Otherwise, if you are not, then you don't need to worry about the same because it won't happen. Frida, what have you done? You can just do in the chat. You have two devices which are on, and both of them are connected to audio. I suspect so. Mm. Oh, you you are together there in the same room. That's what will happen. So if any one of you puts the device on, you will have that feedback. It will be very serious. By the way, all of you are on microphone. So and Charles went off, but you need to realize that it's not quite necessary for you to be able to try and start solving because it's just that we are having two devices which are communicating at the same time from the same point. Though I know some people are actually doing that research to be able to eliminate. You just need to use, I think, some filters so that you're able to get this one out, or that noise will be eliminated. So then we have a study in astronomy. This device can be used, or not the device, but you're talking about the concept of scattering. It can actually be applied in the study of astronomy. Uh, in astronomy, they don't only use they radio waves and microwaves. We use all of them, the electromagnetic spectrum, all the way from gamma rays up to radio waves. They can actually be used in the study of planets, and you also have the study of stars out there. So this is what I mentioned about the meteors and the ionosphere, which can actually be used to transmit signals over long distances. And I think that works for scattering. So the other concept we have is diffraction. And you can be able to see there. So what do we mean by diffraction? Usually when a signal, microwave or radio wave, comes into contact with a sharp object, it will actually undergo what we call diffraction. And you can be able to see what we have here in relation to, I think this you did in high school. If you guys can remember, I think this was with audio. Then also even light. If you actually do something like this for light, it will get diffracted. When it comes out of a small hole like this, it will be diffracted. So you have a wall, then the signal comes and it appears on this side. The receiver is able to get it. The other way you can say diffraction, what happens? A signal appears on the shadow part of the object. That can also be called diffraction. A signal appearing on the shadow part of the object. And if you look at it, a very good example where we are basically having the same is in a building. Currently, you are not seeing, wherever you are, in fact, you are not seeing the transmitter. You're only getting the signal and you're receiving it through your phones. Some of you could be using your laptops. So how does the signal get to your location? It's mostly due to diffraction because that signal will appear on the shadow part of the object there. So even the large buildings, they will have the same effect. Where if you were to draw, actually we assume this is a building of this size, you can also be able to get a signal on the shadow part. And that way your receiver, you actually assume you are located at this particular point, you have your mobile phone and you'll be able to receive the signal there. So diffraction is quite important when it comes to microwave and radio transmission based on that concept that we have mentioned, where the signal appears on the shadow part of the object. So you can also be able to see here we have like something to do with like a hill or even a mountain. So you can see a signal coming, then because of diffraction, it gets to a building on this side where you're able to receive. So that's the same concept. The obstacles. So our signal coming in, then it gets into contact with the obstacle, it appears on the shadow part of that obstacle. And we are looking at the large and big obstacles, which you mentioned earlier. Buildings, we have hills, you can talk about mountains, and so on. So that was the diffraction, and we have been able to indicate the positive effect. But what can be the negative effect of diffraction before you do the positive, before you go to the next concept? You can give an example of the negative effect of diffraction because definitely it also has a negative effect. You can send in the chat, you can talk, but because we are in the same class, I think it's better we write now. I think Remy could be having an issue. I don't know whether he's in the same class. I can see he's trying. The audio is not working for him. So Charles has indicated we have loss in signal, which is correct. Filbert, 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 go to auntie. So loss of signal, degraded signals, that's okay. Interference, that's fine. One more, there is one more, which is very important also. Maybe I can indicate it. I think someone was trying to write. So one of them would be your signal will change direction. Please know that the signal coming down this way, if it was intended to go in that direction directly, it will basically change direction, and because of that, it won't be able to reach the destination. But this is more of a positive effect when you are talking about the signal appearing on the shadow part of the object. But again, we are indicating the negative one is where the signal is not able to get to the destination. But the others are the ones which the members have indicated where the signal is really degraded and we have lost a lot of lost signal that we won't be able to receive whatever you are. And that reduces the quality of service. So dispersion is the next concept. And dispersion can actually appear in two ways. It will be in terms of a signal spreading out from the source. And then the other one is when you separate frequencies. Like this is a concept where you're using a prism and you separate the wavelengths and or frequencies of the different signals. In this case, we are talking about light, and you can be able to see it has the different colors which are diffracted and dispersed from a prism. This experiment you have done it before, but this also happens to even microwave as well. If you are to put a material here which has got the properties just like the prism, it can also separate those frequencies of microwaves and radio waves. So one spread out of the signal as it propagates, and you need to know as it spreads, it will actually be reducing in strength. Then the other one is where we are separating the frequencies. So what will be the positive effect of dispersion? And what will be the negative effect of the same? I think you can send that to the chat. The positive effect of dispersion, negative effect. Yeah, so someone is indicating the dead coverage zones. I think these are the ones which you had for diffraction. Debate had indicated that earlier, which is okay. Yeah, so the positive effect, please note that all the sources in most cases for microwaves and radio waves will actually be a single point like this. So you just have a single point. But then as the signal comes out, spreading, it spreads, which means it will be able to cover a large area. In which case, you are talking about like the locality, maybe some several kilometers. You are going to cover, those that signal is able to cover quite a number of people who are located there, and therefore you are able to receive. The same case, the way we are actually getting satellite communication. The signal from the satellite spreads out. When it gets down to the earth, it will actually have covered a very large area. So that's very good. So it increases the coverage. That's a positive effect. When you're talking about our signals, light, microwaves, and radio waves. What will be the negative effect? You are going to have weaker signals, that's correct? So the signals usually get weaker. The signals get weaker. Maybe I can be able to indicate this. So positive, a wider coverage. As one of them. So negative, you're looking at weaker signals. As of course the signals propagate, they will get weaker. So wastage of frequency due to spreading or dispersed signal. Can we say signal loss due to cancellation? Can we say that this can interfere? It can cause interference. So we have interference. Why? Because if we have another system on this side, the signal coming from this point can be able to interfere with it. So we can mention that interference. I think I believe that that's what members have mentioned: signal loss due to cancellation, wastage of frequency due to dispersed signal. So that's okay, and those could be the main ones that we can be able to pick. So there is the concept of polarization and depolarization. In which case, when you're talking about polarization, is actually the orientation of the signal as it propagates. And we have three of them, three main orientation forms. There is linear, and the linear one can be vertical, you can have it as horizontal. There is circular, we also have elliptical. So circular just traces a circle as it propagates. Elliptical will be tracing an ellipse as it actually propagates. So you can see the way they are appearing there. This one is linear, which can either be horizontal or vertical, but this one is vertical the way it appears. Circular usually traces a circle as it propagates, and then the other one is elliptical as it propagates. So please note that there's one which is here, circularly polarized. It passes through uh, a given material which changes the polarization and becomes linearly polarized. Then it can pass through another one which will also change the directions. It actually makes it unpolarized. Unpolarized means that it's not following some specific trace, like you have elliptical, circular, or linear. So sometimes you can be able to have materials which can have that effect. And of course, there is another explanation which is given here. Though I've given this in terms of light, but please note that it also happens with the other types of signals, which is the microwave and also the radio wave signals. So now, what will be the positive and negative effect of this polarization? So positive. Polarized and depolarization. So the two of them usually go together. Of course, I've explained this one is polarized in a circular manner, linear, but this one is depolarized, which means it's not following a given orientation. So, what is the positive effect of polarization? Any idea? So maybe you might not know. Please know that the transmitter and receiver should always be polarized in a similar way. So it should always have similar polarization for proper reception. Just have Toto go down. I don't want to hear noise. So negative, when you are not using the same or similar polarization, you lose the signal. So the signal is usually lost. And you can't be able to receive it. So this is what usually happens, even when you are talking about the mobile phone communication, radio communication. Just note that if you have a linearly polarized transmitter, the receiver should also be linearly polarized. And specifically, if we have horizontal, both of them should be horizontal, such that when the signal is coming, it's basically received yeah, as it propagates. If this is circularly polarized as it transmits the signal, the receiver should also be circularly polarized. So this is our TX, and you also have our RX. So if you're having linear polarization and vertical, this should also be linearly polarized and should be vertical for proper reception of the signal. Please note that if you don't do that, this antenna won't be able to receive your signal from this side. Sometimes when you are transmitting over long distances, signals will get depolarized. What do you think can result to depolarization as the signal propagates from the source to the receiver? What are some of the causes of depolarization? Like now, if a signal was circularly polarized, it changes to linearly, or if it was vertically polarized, it changes to horizontal, and that way you're not able to receive. What are some of the causes? Some of the causes of depolarization, in which case you are not able to receive your signal properly on the receiver side. So lack of clear line of sight. So in fact, it is about obstacles, and the way you have mentioned it there, so it's basically obstacles. Actually, your attempt is correct. It's obstacles that will cause that, and those obstacles can be of different types. You can talk about the mountains, they can result to that. And they have, please note that like now, if you look at this one, they are indicating it has a given property, which will change the circular to linearly polarized. And then you have another one here, which is a material, of course, that has got some properties and depolarizes the wave as it's coming in. So those properties of the obstacles are the ones which will result to those effects. You need to note like the Earth's surface has got some properties. In most cases, when you're transmitting vertically polarized signals, they reach a point where they start changing polarization. Then, as they are changing slowly, they get to a point where they become horizontally polarized. So you see, gradually changes from vertical polarization to horizontal. In this case, the receiver won't be able to receive the signal. So you actually lose it. And you realize this what happens, like now when training and antennas, receiving of TV signals, you guys you realized when training, most of the time you stop receiving your signal. If you are not in a place where actually the signal is very strong, it will be affected. Anyone who has experienced that, when training, sometimes you lose the signal. And yet the antenna is there. Yeah, so cloudy also, weather will actually interfere with the signal, that's correct. When using satellite dishes for free to air TV, that's very correct. So I think you guys you have experienced that. And please note that the antenna is there, but you're not receiving. In most cases, what happens is the change of orientation of your signal, and that way you're not able to receive it. How do you think you can solve this? What can you do to solve such problem so that you're able to receive your signal properly? Please know that you are going to do design. The antenna designs should incorporate such. In fact, you can have what we call diversity in space. We usually call it in space diversity. And as a result, the antenna can actually be able to receive a signal which is maybe horizontally polarized and also vertically polarized. So it's all about the design in most cases because naturally it will still occur. Rain will actually be there. You can't be able to maybe say that you're going to eliminate it. It will be there. The only thing that you do is with the design of your antennas, your receivers, and transmitters. So I think let me see whether I can get a video which can show us this kind of representations here. Circularly polarized, elliptical, and also vertical. This software we are not able to share everything. It can only be able to share the videos, and this is just a GIF. It's not accepting. So did you? Usually Zoom actually I could be able to share everything and you can see, but this one is a bit. It's not that quite flexible. So as we get that, yeah, you can use Ubuntu's laptop. That's okay. So just use it if you can be able to access it, and show us. You can share. You can actually share the screen. Then we get to absorption. So absorption is basically the concept where when you are transmitting your signal, it comes into obstacles, it transfers the energy to the same obstacles that it has actually come across. Members can copy that, and you can be able to basically show. Yeah, so that's what I wanted you guys to actually check the way the signal is moving when you are doing the different polarization methods that we have. So linear, the first one, circular is the second one, and elliptical is the third one. The linear one there is not vertical. Actually, one can make it vertical, you can make it horizontal. There's no problem, but that's how it works. And I think that's fine. Thank you for the sharing. So we can just continue with the other one. So I was talking about absorption, and I indicated that the signal gets into contact with an obstacle, and this obstacle has got some properties which are able to take in some form of energy. As it gets across to the other side, it will have left some energy here. And that energy is basically in terms of heat energy. In most cases, it will actually be in terms of heat energy. So the transmitted wave, the one which comes out of that medium or the obstacle, will be less in energy than what we had when it was coming in. That happens a lot in space. Then I think sometimes you're talking about a concept which we are using spectroscopy techniques. So sometimes this can be applied in many applications. You can actually use it in the study of materials. You can use in the study of different media when you're talking about absorption. So in chemistry, that's what we are talking about. You can actually be able to use that in infrared and UV in this analytics. So you're going to have across how you can have these systems which are used out there for this function. So molecular physics, molecular and atomic physics, that study, and that's what you are calling spectroscopy. So it can also work with microwaves and radio waves with some systems, in which case when you are talking about the wavelength, it will actually be given by this formula. I think you have come across it before. It is the same as the one we had earlier, where we were talking about energy is equals to HF. You can remember that formula. It's the same, it's not different. It's only that we have actually taken frequency in terms of wavelength and speed. And then this energy, it's usually one form of energy, subtract the other one, to give us the energy difference, which comes to H. And then if you are using the speed, you just divide by wavelength to get that frequency. In which case now, with this one, you have gotten the wavelength as the subject of the formula. So that's what they use in the study, spectroscopy. So molecules of some materials, and I think you've heard about the same. So such kind of systems can also come in, and we discussed about them under spectrum management. So the last section will be on free space losses, which are equivalent to what we talked about up there as attenuation. But this one, I want you to look at it differently, because it affects quite a lot when it comes to the use of microwave systems, wireless systems. This is usually a very important concept. It's the one which enables us to put repeaters in some specific locations. The one which people have studied, indicating that if there is an obstacle somewhere, it will affect your signal as it moves. So the lowest level that we can get, please know that as the signal propagates from the transmitter to the receiver, so I will take my transmitter here and then the receiver there. So we have a distance between the two, which is given by D. Usually the received signal, we usually call it PR, is given by the divide by 4 pi D squared. When you incorporate the properties of the antennas we have in the transmitter and the receiver, and the frequency of transmission, you are going to have the effect of distance, the effect of frequency, and also the effect of obstacles. But when you are looking at free space where there are no obstacles completely, this will be what we have as the losses. So I wouldn't want to drive this equation because I think at the moment we just need to know how we use it. So these are usually what we call the free space losses. They are given by 32.44 plus 20 log f plus 20 log d. Please note that f is the frequency and d is the distance. This 32.44, because this is in terms of dB, of course we are using 10 log somewhere, which I believe we must have talked about at some point, at the logarithm function. It incorporates the frequency and also the speed, this value. But just get hold of it as the losses, free space losses are usually given by 32.44 plus 20 log f plus 20 log d. This 20 has got a bearing with the power 2 that we have here. So it brings it out actually. So our frequency will be in terms of megahertz and also the distance is in terms of kilometers. So we need to get this. But if you are interested in getting the derivation, you can be able to get, I can be able to get it for you. How you drive it up to a point where you actually get to the losses being given by this value. So, but at the moment, I just want us to use that formula. And then if we have an example here that is actually being done. So what are we supposed to do? We substitute the value of frequency here. We also substitute the value of distance, and we're able to get that comes to that 2.44 plus 20 log 2 times 10 to the power 3. Where are we getting 2 times 10 to the power 3 from? So I think this is supposed to be 2 gigahertz, not 1 gigahertz. So 2 gigahertz is how many megahertz? It will be 2000 megahertz. And if you put the value 2000, 2 times 10 to the power 3 here, you need to confirm whether the answer you are getting is actually given by 98.46. You confirm from your calculators. Yeah, so it's 98.46. Please note that this value is 2 gigahertz. That's what will give us that. Then someone can ask you a question, determine the losses for a Wi-Fi router, the routers that we usually use everywhere, providing us with Wi-Fi signals at a distance of 200 meters. So how do you go about calculating this? You need to note at what frequency the Wi-Fi is transmitting, and this will be at 2.4 gigahertz mostly. So introduce the frequency in the F value here variable. Then you also bring in 20 log 0.02 because you need to convert this to kilometers. We said distance is in kilometers, frequency is in terms of megahertz. And if you use your calculator, you'll be able to get 66.06 dB. Please confirm that. Maybe I need to give you another one. So change this to mobile. Two hundred meters is supposed to be 0. You divide by 1000, it's 0.2. That's correct, 0.2. So the answer here is for 0.02, I believe it is. So maybe we can take this to be 20 meters so that it comes to the exact value of 66.06. You can confirm also. Yeah, the one for 0.02 is the one which will give us 66.06. So put 20 meters here. Now, a mobile phone, someone will ask you a mobile phone, and we are looking at a distance of, let's have 600 meters. So please, can you calculate for me that? Get me the losses. For the mobile phone, you can use the latest. Let's use the 2100. So someone could use the 800, 900, or 1800, 2100. Yeah? So let's use the 2100. None of you was calculating. So I'm wondering where you are getting your value from, because me I'm getting 94.44 and 4.45 decibels. What did you use? Have you used 2400 or 2100? Personally, I've used 2100 here. I suspect you guys you use 2400. Good. Yeah, you need to indicate the 20 log 0.6. That one, then I believe if you do that, you will actually be able to get it correct. So, um, you've confirmed it's coming to this. Yeah, so after confirmation, how do you think this would be varying with distance? Let's take distance variation. Assume we are increasing the distance from 0 to a given value. Graphically, what do you think we are going to have? The graphical representation of this. So please know that if you are plotting, your graph will appear this way. That is the losses. So with respect to distance, as you're increasing your distance, the losses are also increasing. That's what happens. But now, if the losses are increasing, what will be the received signal? And usually it's given by this formula. The received signal in terms of decibels will be the transmitted signal, take the gain of the antenna that will be receiving, plus the gain of the antenna that will be transmitting, minus the losses we have been calculating. So an example is also done here. Determine the power that is received at 20 kilometers if the transmitted power is 100 milliwatts. So with this one, you can take your gain for the transmitter and the receiver to be the same and same as 4 dB. 4 is usually very common. So please calculate for me the received signal based on this formula. I've given you all the parameters, the gain for the transmitter, the gain for the receiver. The distance is 20 kilometers, the transmitted power is 100 milliwatts. I want you to assume the losses to be the ones that we've just calculated for the mobile phone. No, I think no. It will be different because of the 20 kilometers. So use the frequency of 2100. A distance of 20 kilometers, then the other parameters will be given that way. So which means you need to start calculating the losses, which will be subtracted from the summation of the transmitted power in decibels, the gain of the receiver, the gain of the transmitter. I want to see whether there is anyone who will get that question right. So please make sure you change your power from just power to decibels, and that will be given by um, 10 log the brackets 10, that's 100 times 10 to power negative 3, which will be the same as mbona haka mtu kanalia hivyo na mko hapo? Or this one? Yeah, usually when you are calculating power in terms of decibels, you need to use 10 log always. Whatever value that you have here, if it's power, it will be 10 log. If it's voltage, it is usually 20 log, and current. So it's a constant. It's just something which is a standard. When you're changing from the actual values to decibels, this is what you use. Maybe I should have done some bit of introduction on the same. I think I just went straight, assuming that we know some of these parameters. Is that okay? Yeah. Yeah, please log off the class. I just do some things more here. I complete the question. Then when you look at it in the video, you can be able to get it clear. Next week, I think we are meeting physical, so I can also try to sort out an issue which might arise. Is that fine? So the transmitted power in decibels will be given by negative 10 dB. That is when you calculate. That's what you're going to get. And then the losses will be given by 32.44 plus 20 log our frequency is 2100 plus 20 log distance of 20 kilometers. So that comes to 124.9 decibels, which means I can be able to now take the received power PRDB to equivalent to the transmitted power is negative 10 dB, then plus 4 the gain of the receiving antenna, plus 4 the gain of the transmitting antenna, minus the losses, which is 124.9. So effectively that value will be given by 126.9. Decibels. So that's basically the results of what we are calculating. Actually, it's negative 126. Which, if you want to transform into the power, actually you need to use this formula to go back. But it's basically negative 126.9 decibels. It's a very low signal, this one. In which case you might not even be able to feel the effect. But if you reduce this loss, maybe you talk about like a few kilometers. In fact, if you take the one we had for um, 600 meters, that was 94. Though still it will be quite, it's high still, not so low. But usually for Wi-Fi, okay, microwave. When you're talking about mobile phones, they will still be able to use or to transmit over this kind of distances, depending on the environment. Because if you have outdoor and you are talking about urban, then 20 kilometers is quite long. But if you are looking at rural, this is just enough. So there are some wireless communication propagation modeling concepts which we talk about, which are based on what you have actually discussed. These are able to give us the signals which are received as particular points, depending on the obstacles which are available and also the environment. Many researchers have worked on this, and they have come up with quite a number of formulae which you are able to use for wireless transmission or wireless communication. And those methods, there are a number of models which are divided in three categories: deterministic, empirical, and combination of the two. For deterministic, usually we're talking about you are getting a specific output when you give it a set of inputs. It won't change. But empirical, you are looking at a situation where the value at the output can actually be able to change according to the environment that you are looking at. You can get a set of inputs. Then when you look at a different environment, the output becomes different from what you expect. So this is usually through experiment. By the way, most of these are usually obtained through experimental work. So they have given a number of examples, but the ones you might be interested more on is the ones under empirical. We are looking at the one slope model, the dual slope model, the multi-wall model, the average wall model, the cos231 ATA, that is CH, and the ATA Okumura models. Then an hybrid of the two takes the advantages of the two concepts, the accuracy of the deterministic and the simplicity of the empirical. Because deterministic models are usually quite accurate, then the empirical ones are very simple. They're just based on experiments. Resources are usually consumed with the deterministic one, more resources as compared to the empirical methods. So the course 231 was actually developed by a given consortium given by these initials. And then one slope, it's basically the one we've just done. It's actually the same as the formula that we had for the losses, which you have been using, free space losses. It's only that in terms of mathematical representation, sometimes you also give it in this form when you are giving a reference point, which is 1 meter usually. So the graphical representation will be like this. If you are using MATLAB, this is what you actually get. The plot, though it is simpler, you will just be able to take the parameters input, then you put the formula, and you're going to get these graphical representations. The others are just to add maybe the grid, the x-axis, the y-axis, which is basically the distance, and this one will be the loss. Then this is the received power. Please note that when you are talking about received power variation, it will always be like this. Losses variation will always be like this as indicated. It increases exponentially, this one decreases exponentially. So the dual slope picks two slopes. You use one loss up to a given point, then introduce another one from that point to the last point. And the graphical representation will be like this. You can see there are two of them. So this one uses one loss, and the other one uses a different loss from what we have in the single slope. The single slope is everything up to the end considered. So the losses will be given this way, then the reception or the received power will also be represented this way. And this is the plot, the code MATLAB, which will generate us these plots. The partition model takes many partitions, not just two. Where of course this one, as indicated, is the loss at 1 meter. Then it will do from 1 meter to 10 meters, 10 meters to 20 meters. We have a different loss 20 meters to 40 meters, and one above 40 meters. So all of them are different losses, which are usually considered. And then they give us, okay, from the MATLAB code, which is generated from that formula, and the graph will actually appear like this. So that will be the graphical representation for the partition model. You can see there are actually four of them. One, two, three, four. There are four of them. And then this will be the received signal. So the others, which you also have, the multi-wall, which means you are taking a number of walls. The cost 231 ATA model to also have metropolitan and suburban. There is the Komura ATA, which picks for us the urban area, suburban area. We also have the rural area, and you'll be able to see those graphical representations in terms of, all these are actually in terms of the received signal. Then there is the one slope with a random variable. Most of the time our signal will be random, and this is also a depiction of the same. So that's what you can mention about the losses and the modeling, which usually happens with this. So we'll be able to use some um, mobile app, which can actually, you can be able to use to see on how the signal varies with distance. As you move away from the transmitter, the signal will also be reducing, and it will actually be appearing in this manner, which is usually a random representation, but reducing with distance. So, and that's all about the effects on signals, which are the microwaves and radio waves as they propagate.